Hello everyone, it's 1 p.m. sharp and we are starting our webinar of Global Reach number 51. Today we have a talk by Manolis Georgoulis, who is research director at the Research Center for Astrophysics and Applied Mathematics of the Academy of Athens, Greece, and scientific editor for the American Astronomical Society Journal. His Bachelor of Science degree in physics is 1993, PhD in 2000 in solar plasma physics from Aristotle University of Thessaloniki, Greece. He specialized in heliophysics with emphasis on solar magnetism and the initiation of solar eruptions. Extensive work has been done in solar flare predictions and space weather forecasting. He is project coordinator of the FlareCast EU Consortium and project manager of the ESA SSA SWEA effort service, among other projects in Europe and the USA. He is a former national delegate of Greece in ESA's Science Program Committee and president of the European Solar Physics Division of the European Physics Society. He is sitting president of the Commission E2 Solar Activity of the International Astronomical Union, local organizing committee chair for COSPAR Athens 2022, implementing the 44th COSPAR Scientific Assembly, Greece national representative in COSPAR. He is author of almost 100 referenced papers, including invited book chapters and monographs, and 53 papers in conference proceedings and special volumes. Editor in 7 fully refereed topical issues and books in solar physics and space weather. He had more than 3,500 citations with NASA ADS-H index of 34 and 1,000 more in Google Scholar with H index 41. So please, Manolis, go ahead. You have your 45 minutes. I will issue you warning 5 minutes before saying. Yeah, go ahead.
Thank you, Gregory. Good afternoon for those who are attending from the States. Good evening in Europe and in Asia. I am really happy to be here. It's a pleasure and honor to be presenting you a seminar today in this well-known series. I have seen the list of talks, and it is amazing. So I can only thank Gregory for this great effort of capturing a number of key talks in solar physics and related subjects and placing them online. So I'll be talking today about, as the title implies, about the whys and the hows of solar eruption prediction. As you have guessed, the talk is divided in 2 parts. The first part will be talking about the physics. Why is that we believe solar eruptions are interesting, and what are their impact, their repercussions to our well-being here on Earth and to our space exploration program. So in essence, I will be pitching, although we are convinced that we need to find a way to predict solar eruptions. I'm preaching to the choir over here, but nonetheless, I will try to make a brief case. Why do we need to predict solar eruptions? And then the second part of the talk is going to be on the how. What are the elements that we have, and what are the elements to be desired to reach a possible prediction that is credible enough to be used in our future endeavors. So in terms of the whys, at first, I will start with solar flares. So I'm not going to talk about small-scale activity in the corona. I'm going to talk about these big events, these big eruptions happening in the solar corona. And I have used here a pretty popular definition of solar flares coming out from the American Heritage Dictionary. These are just bursts of magnetic energy released near the solar surface, associated to sunspots, and accompanied by bursts of electromagnetic radiation and particles. they essentially flood the entire electromagnetic spectrum. Here is one typical example that is also recent. It happened less than a couple of months ago in March 30th. You will have noticed that the sun has started picking up in terms of activity. So this is an X-class flare that happened on March 30th. So how do flares happen? It can only be the reservoir of magnetic energy in some parts of the corona that fuels flares. They can't be happening because of anything else, any other energy factor in there. So in essence, what we have is that before the flare, we have the magnetic energy in that volume that will become the flaring volume. And then we have the magnetic energy in the same volume post-flare, after the flare, plus a certain energy, the difference between the two energies. We have less energy after the flare because we need energy to power the flare. This energy will be given to heat, namely to collisions in the plasma particles, to electromagnetic emission, and to acceleration of some privileged particles that will become the accelerated, the relativistic particles coming out of the flare. The flaring volume is relatively small with respect to the coronal volume, so the whole thing is happening at the localization of the corona. Now, if you look a bit more into the energetics of the solar corona, active region and quiet sun alike, then you will notice that we are dealing with a base energy level, which comes from the so-called vacuum magnetic field component, the one that does not require plasma, and the second component that does require plasma, because it depends on the electric current density and on the vector potential that gives rise to the magnetic field that is due to the presence of the plasma. So this is what we call the free energy. And the energy that is released in flares is always smaller than the free energy in that flaring volume because of a good number of reasons. So it cannot give more energy than the one available, but it does not even give an equal energy to the one that is available. You always have some free energy left because you have plasma. So sunspots and flares because of sunspots. The first flare that was observed by Lord Carrington back in 1860, you can see the historic picture of the sunspot and a sketch of it on your left. So we are talking about sunspot complexes with a lot of free energy accumulation above them. This is where major flare happens. And these sunspot complexes are known as active regions. Then in the 20th century, after the realization that sunspot complexes were actually due to the magnetic field by George Ellery Hale and his seminal work at the beginning of the century, people started trying to measure these magnetic fields. And what you see on your right over there is sunspot observations, magnetic field observations in sunspots that have collocated in time with flares. These are coming by historic observations of the Crimean Observatory, Solar Observatory, and the paper in Annual Reviews in Astronomy and Astrophysics by Severny. He was talking about strong linear polarization signals collocated with the flares that implies strong transverse field on the solar photosphere. By transverse meaning perpendicular to the line of sight. So these were seminal observations and seminal results. So that was one flare. Flares happen in swarms. They can even happen in swarms of big and smaller events at times of high activity, heightened activity in the solar corona. This is one such example in 2011. As you can see over here, the results are coming from the SDO AIA telescope on the left, and on the right you see the spectral irradiance at soft X-rays as detected by the GOES satellites. And then you can see the different flares picking out. and the different levels that are characterized, that are defined by the horizontal lines that you see in there. So how do we make the free energy released in the corona? Well, we have the undisputed, I would say, mechanism, although there was some dispute several decades ago as to how this mechanism was happening, was magnetic reconnection. So what you see over there on your left is the first proposed magnetic reconnection scenario by Sweet and Parker back in late 50s. And then in early 60s to mid 60s, there was another scenario that appeared to be improved because it gave rise to a faster reconnection and energy release proposed by Petschek. These were summarized by Eric Priest in his well-known book, Plasma Astrophysics, in 1994. And then this main mechanism of magnetic reconnection was implemented into what we call the standard flare model that started in early 60s to late 60s to early 70s in 2 dimensions, and then was evolved like what you see over there in the right to become the standard flare model in 3 dimensions by Miho Zambier and colleagues. So this is a way facilitating magnetic reconnection. And then if you just leave flares aside as certain occurrences and you try to see the statistics of these events, so you take several of these events and you put them on occurrence frequencies, then you come up to a stunning conclusion that you can see over here by Drake back in the early 70s. You have power loss. You have well-defined power loss with whatever expression of size you take for flares. So you have self-similarity at first. You have flares that are more rare as their size increases, any way you measure size, and become more frequent as their size decreases. How this self-similarity comes to be, this is something that we see in pretty much every solar cycle without loss of generality. This is a compilation of cycle 23 over here. You have the so-called C-class flares, GOES C-class flares that are measured in several thousand for a typical solar cycle. Then you go a decade higher to M-class flares, in which case you're talking about several hundred. Then you go a decade higher to an order of magnitude higher to X-class flares, in which case you're talking about 100 events per solar cycle or thereabouts. And then the great flares of X5 and above, you're talking about a few of them, a handful of them, less than 10 at a typical solar cycle. And in the pie chart below, you see the percentages of active regions giving rise to these events. So we are talking about a very eclectic event in terms of occurrence frequency. The higher the size of the event, the more rare it becomes in a self-similar manner. This is what statistic means for flares, statistics. The first interpretation of flares happened by Roster and Vaiana back in 1978, in which case, in order to give rise to the observations of Drake, to interpret the observations of Drake, they assumed that flares were random and independent events, obeying Poissonian statistics. What you can see over there is a probability of a flare happening. I hope you can see my cursor. This is a probability of a flare happening as a function of the mean occurrence frequency of flares and time. Working your way through from there, you can come up with a size distribution, a frequency distribution of the energies of these events that appear to be giving rise to power loss with a spectral index that can be changed accordingly to the conditions. Now, this was interesting and important because years later it was facilitated as a key reason why active regions in the sun are not only self-organized systems, but self-organized critical systems, giving rise to flares. This was an appealing idea that was first applied to flares in the early 1990s, and I will show you an example. But I'd like to give you an aphorism over here that was known back then when the first self-organized criticality papers came out. This aphorism was that these are stochastic events. So if you try to predict them, you're going to go into trouble. They are hardly predictable. In terms of flare applications, we had flares being coined as energy avalanches in the early 1990s by the works of Ed Lu and Russell Hamilton. And then a few years later, in Thessaloniki, we quoted flares as elements of great spatio-temporal fragmentation and clustering in small and large structures, and we called them the statistical flare in our cellular automata simulations of flares. That also gave rise to power laws similar to those of the observations. This is just a few elements about flares. Then in the mid 1990s, there was this big debate under the so-called solar flare myth. So there was a paper in 1993 by Jack Gosling saying that the popular perception of the relation between solar activity and interplanetary and geomagnetic events is wrong. There is good evidence that the central role is played by what people knew since the 1970s as ejecta coming out of the corona, known as coronal mass ejections. And this actually provided quite a bit of locomotion in the solar physics community and even forced Zdenek Zvezka in 1995 to write a paper talking about that the solar flare myth is a misunderstanding because we now have the term eruptive flares that associates flares to CMEs, to coronal mass ejections. So what is a coronal mass ejection? Again, a popular definition by the American Heritage Dictionary. It's a bubble. It's a massive, and I mean 10 billion tons of plasma bubble shaped out and jettisoned, ejected away from the sun that also heats and accelerates particles as it goes. Okay. Now, CMEs are not the same beasts as flares. Flares are just the electromagnetic emissions that are happening due to the release of magnetic energy. What are CMEs? Well, you have CMEs coming out both from active regions and from the quiet sun. If they are happening in active regions, then they definitely associate to flares. However, not all flares, even major ones, are associated to CMEs, even though the larger flares are more likely to associate to CMEs. And if you go, if you see in that plot over here, if you go above X2 or X3 class flares, then you have essentially a one-to-one association between flares and CMEs. Now, active region CMEs are faster because they are more energetic. There is more energy to fuel them over there than in the quiet sun, in which they are slower. And that's a characteristic CME, so that you get the idea of the bubble. You have a flare happening in the sun. This is a composite observations by AIA and Soho Lasko, and you have a first burst and then the main burst coming out. And you see this kind of interference on the detector that has to do with the accelerated particles of the CME, and I'm going to talk about that as well. So you already heard the term eruptive flare as opposed to the plain vanilla flare, to the plain flare that people are talking about since more than almost a couple of centuries now. What makes a flare an eruptive one? And this is already a vast topic of debate in the literature. You are talking about thousands of papers, tens, if not hundreds of volumes talking about that fact. And there have been several groups and several reviews on this topic. I am putting just a few over there on your right-hand side. But I would like to point out to something that appears to be changing the paradigm. This was a review coming out by an ISI, International Space Science Institute team, a few years ago. That was led by Spiros Patsorakos and Angelos Vourlidas. So the literature was summarized saying that we have two elements in the pre-eruption phase. We can have two possibilities in the pre-eruption phase. We can have a sheared magnetic arcade and a magnetic flux drop. I don't have time to go through the details of what each one of them is, but a magnetic flux drop appeared to be a more intricate structure with a lot of intertwining of magnetic field lines. And moreover, you can have a hybrid situation of a sheared magnetic arcade and a magnetic flux drop over there. So the common element, the common denominator between the flux drop and the sheared magnetic arcade is what we call a polarity inversion line, a magnetic polarity inversion line in the solar photosphere, which is a close accumulation of both polarities of flux. We can measure the photospheric magnetic field. We cannot measure routinely the magnetic field vector above the photosphere. Hence, all this debate of what is the case of the three-dimensional magnetic fields above the photosphere. So you have measurements on the photosphere and models above it. And this is why you get this kind of debate, as I said. So you can have both. A magnetic arcade, a sheared magnetic arcade, and a magnetic flux drop above the photosphere. And these configurations can be erupting via a variety of different mechanisms. I'm just putting the names over here. You can find all about them into the reviews that you see on the bottom. We have at least 6 of these mechanisms that factor different physical mechanisms and different physics overall. So in this review by Spiros and company, the key conclusion was something that might even change the paradigm, at least as far as I can see it. It says that the differentiation of pre-eruptive configurations in terms of magnetic arcades, sheared magnetic arcades, and magnetic flux drops seems artificial, because observations and modeling can be made consistent if we are talking about a hybrid evolutionary state, in which case you start with a sheared magnetic arcade and you end up with a magnetic flux drop. And there was a key observation over there in your left-hand side, in which case you see a confined flare, namely a flare not associated with the CME, giving rise to an apparent magnetic flux drop and a hot channel in the corona. That was published by Spiros Patsorakos and company about 10 years ago. And on the right, you see another situation in which we are monitoring the mutual and self terms of helicity along a polarity inversion line. And there you see that you have a close correspondence between what we call the self-magnetic helicity, namely the twist and writhe, and the mutual magnetic helicity. And based on a certain reasoning, we have associated these to a conversion between mutual helicity and self-helicity. So all in all, what is helicity? Helicity, very, very simply, is a metric of complexity, is a measure of complexity in a magnetic configuration, magnetic helicity in this case, that deals with a self term. If you're having twist, if you're having writhe, if you're having torsion, then you're talking about a structure that is self-helical. And then if you have several such structures close to each other, you have a mutual term, pretty much like an inductive effect, give or take, because there are meaningful differences in there. But nonetheless, you have a lot of mutual helicity along with some self-helicity. And then what happens is that you get a conversion of mutual helicity to self-helicity. This conversion is resistive, and it can happen via magnetic reconnection, which is the example that you see over there on your left. So in essence, you start with a polarity inversion line. You have conversion of helicity, you end up with confined eruptions that give rise to magnetic flux ropes, either full or hybrid ones, partial ones with sheared arcade, and one way or another, this thing will erupt at some point. But why do you have this conversion of helicity, and why do you have this evolution along polarity inversion lines? This is a little bit of a semi-theoretical approach. What you see over there is some idealized sunspot pair on your left, and the interacting sunspot pair that gives you a strong polarity inversion line. And then you get shear. Why do you get shear? Well, we claim this is happening because you have a strong tension force because of a broken symmetry in there. Broken symmetry meaning that you start having net electric currents that are perpendicular to the magnetic field, so you have a J cross B factor that's going to give you a Lorentz force. And if you have strong flux along the polarity inversion line, then you have the Lorentz force actually dominating the plasma, even in the photosphere, and moving the plasma. In this respect, you end up with a shear along the polarity inversion line. And when you have a shear, you start having everything else. You have a lot of resistive evolution, a lot of confined magnetic reconnection in there that's going to take the huge mutual helicity of the arcade in the polarity inversion line and effectively start converting it into self-helicity. Then the different reasons, the different ways we have to measure helicity in the solar corona, in active regions and beyond. I don't have time to go through all these mechanisms, but what I can tell you is that first we observe helicity in the corona. This is a CME that is clearly helical. And this is the initial stages of an eruption, an eruptive King instability published by Dave Rust and Barry Labonte about 20 years ago, in which case you can clearly see helicity in there. Then different works by Alexander Nindos and Mike Andrews show that helical active regions appear to be eruptive, whereas less helical active regions appear to be confined, give rise to confined and/or minor flares. What you see over here in the center is the so-called energy helicity diagram that talks about critical thresholds. Critical thresholds in terms of magnetic free energy and magnetic helicity, above which the majority of active regions are eruptive. And in a seminal paper by Barry Labonte and company back in 2007, it was clearly shown that major flares came from active regions with a lot of helicity. And not only that, over there in the bottom, you see the CME wind-up time. You get to have more CMEs for active regions with a lot of helicity within shorter waiting times. So helicity is there. But if we go back a bit on the photosphere, just to give you an idea of the example, you have there a magnetic evolution, and you can end up with a very complicated situation. So all in all, you have the formation of sunspots over there by magnetic flux emergence. You have the polarity inversion line formation. If you have strong polarity inversion lines, and by strong I mean quantifiably strong in terms of equipartition values of the magnetic field in the photosphere, then you have net electric currents, in which case you create a Lorentz force that provides an irreversible evolution. This Lorentz tension force is going to be creating shear along the polarity inversion line. There will be self-helicity accumulation and conversion over there because of the shear, and at some point the whole thing will tip and will give you an eruption, at least one of them. You may have the same situation happening in case you have a continuing flux emergence and more eruption in the active region, or you may have at least one eruption and then the dissolution of the active region when the energy and the helicity just shed away or convected in other parts of the sun. Most active regions, the majority of them, go up to step 2 over there. They give you a polarity inversion line because they have two polarities, so it might be a weak, it might be a disjointed polarity inversion line, but not a strong one. If you create a strong polarity inversion line, then you create a point of no return. This is exactly why we have we have called the formation of strong polarity inversion lines the point of no return. So this is what is happening, at least in our idea, with eruptive active regions. That appears to be aligning with the findings of the discussion of the EC group led by Spiros and Angelos that I told you before. But not only that, you don't only have flares. As you know, we have CMEs. If CMEs are fast enough, faster than the ambient speed in the inner heliosphere, then you have shocks. And whenever you have shocks, you have particle acceleration and the so-called solar energetic particle events. So all in all, we are talking about a pyramid here, a pyramid, I would call it the pyramid of the intense space weather. You have active regions in the solar photosphere, you have flares happening above active regions, you have CMEs, and you have the tip of the spear, which is the SEP events. Putting them all together in this very nice simulation, you can see that we have the Parker spiral. In the inner heliosphere, we have disturbances, namely CMEs. Flares do not have a directionality because they are photons propagating radially. However, CMEs as well as SEPs have a very clear directionality, so it depends. The temporal profiles of events, as you see them from different vantage points in the heliosphere, are going to be very different from each other. So all in all, we are talking about flares happening at some point in the sun, or you might have the structure giving rise to the CME being destabilized first and giving rise to flares. This is something that is still TBD. But the first thing you're going to see at 8 minutes or so after the flare is the flare photons. So there is no early warning for them. You see them as they arrive. Then in about 20 minutes, in case there is good magnetic connectivity in the inner heliosphere, you start seeing the first accelerated particles. And then in the coming day or two, you have the CME shock accelerated particles and the CME itself. The whole thing, the whole part of space weather that relates to solar eruptions is vast in the sense that it extends over 8 orders of magnitude in both space and time, either way you get to it. So in order to be able to get the whole thing from sun to earth is an intimidating task that deals with a lot of cross-scaling in both space and time and huge differences. So in terms of repercussions, in terms of the impact of solar eruptions, what I have over here is an excellent report by the National Academy of Sciences in the US, in which case we have the socio-economic fabric simulated by a bunch of peons, a bunch of blocks over there that appear to be connected non-linearly in an inherently non-linear way. So imagine any of these blocks going down because of extreme space weather. Then you're going to have unforeseen effects because there is no prior scheduling on how the different blocks are connected. For example, if there is a lot of activity, geomagnetic activity due to extreme space weather, you may find yourself unable to draw money from an ATM simply because the ATM will have a non-operating GPS, so that it will not be able to make sure that it is in the location that it should be. And in this case, it's going to go into a safe mode and just will not be able to operate until things become better. So in this case, you can have repercussions that you can hardly imagine. In terms of biological repercussions, again, I am preaching to the choir over here. We are talking about issues, even life-threatening situations for astronauts, either in extravehicular activity in the International Space Station or in the envisioned missions to Moon and Mars. But even much lower and closer to the Earth, if you have extreme geomagnetic emission due to extreme space weather, then at least in a couple of cases that we know of, international airliners that were operating intercontinental trips, they had to change their way. They had to shift ways to avoid passing through the poles. So all in all, we need to learn how to predict solar eruptions. And I'm getting there briefly. What I talked to you about is if you wanted to predict solar flares and eruptions in general, then we need to predict the class and the size of flares before we actually observe them, before they actually happen, because when they see the flare photons, they are already here. We talk about CMEs, then we talk about the time of arrival and the geo-effectiveness, so their profile and their characteristics that will give us an idea on whether they will be able to trigger geomagnetic storms at Earth. If there is no CME, then we need to know whether there are going to be any SEP events, in which case we need their flux and fluence. If there are coronal mass ejections, then definitely we want to know about SEPs and their temporal profiles, as well as the time of arrival. And we have to do this in a situation of data, as you see on the right-hand plot over there, that has increased by 7 orders of magnitude over the past 40 years. So this is a classical definition of what we call a big data environment, an ecosystem. We have to browse through the data, all these data, in order to be able to predict solar eruptions. And how do we predict, in essence? Well, in the simplest possible case, we are talking about a Boolean, a binary prediction, a yes or a no, or we are talking about a forecast probability going from 0 to 1 for a forecast event. In case of a binary prediction, we can have a yes or a no, as I said. If we do it many times and then we check how we have done, we can have this very simple contingency table or confusion matrix by some other people, in which case we ask ourselves how many times did we manage to correctly predict, how many times we missed in terms of a false alarm or a false negative, and how many times we predicted that nothing happened, and indeed nothing happened. So this little thing gives rise to a great deal of metrics that can be used for performance verification. If we are dealing with a probabilistic prediction, then we have a probability, a forecast probability that we compare with event frequency. So the closer you are on the diagonal of this so-called reliability diagram, the better the work that you're doing for forecasting. Some history. We have sunspot classification by Macintosh, and we also have tables of association of different sunspot types with solar flares. Peter Gallagher and company, back in 2002, 20 years ago, they took the Poissonian distribution and they managed to come up, based on also information about sunspot types, they managed to come up with a flare probability, at least one flare for the next 24 hours. This is the method behind the solar monitor tool that many of us know and have used quite frequently over the past several years. The whole thing is, just to see the big picture again, the whole thing is to be able to distinguish between populations of active regions, the flaring or eruptive populations and the non-flaring or non-eruptive ones. You can do it via Bayesian analysis, you can do it via principal component analysis, or linear discriminant analysis, or even non-linear one. These are some ideal plots over there, in which case you see, particularly on the left, an ideal differentiation between different populations, not active regions, but just a generic example there. And on the right, you see some of the main probabilistic background to get to there. Here are some initial results of this effort to distinguish between different population of active regions. You see that these results leave a lot to be desired. There is a lot of mix-up between different populations. So clearly, there is a need to get better and to do better things. This is a top-level example that I found from a data science website, and I liked it very much, and I adapted it for solar flares. What you have over there is 3 different edges on that triangle. You have the confirmatory edge, you have the predictive edge, and you have the exploratory edge. In the confirmatory edge, you ask yourself whether the photospheric features that you can calculate from the magnetic field on the photosphere that you can measure can give you an idea, can give you an association or a correlation, with flares. This is purely statistical. In order to be able to get predictive, these people claim that you have to go into elements that are more sophisticated, like machine or deep learning. And moreover, you can go further into the exploratory component and see whether you can use self-consistently whatever you're doing for flares to extend into the forecasting of CMEs and SCPs. This is, by the way, what the Flarecast project stepped on some years ago.
Manolis, you have 5 more minutes.
Yes, thank you. Thank you, Gregory. So in terms of machine learning, you can have supervised, unsupervised, or hybrid. You ask yourself whether computer can build automatically with experience and what are the fundamental laws that are doing this kind of thing. In terms of deep learning, you have black boxes to deal with, so this is the price you have to pay, but you have a better performance if you have more data. And by more data, I mean orders of magnitude more data. And the question here is whether we have this kind of data and how do we interpret those black boxes. So just to give you a big picture, the way some people think about this problem is the same way as if we are having a theory, right? What does a theory mean? A theory means that you have a hypothesis-based idea or notion or concept and you want to test it. And to test it, you get some data, you get a forecast model, and you try some verification of this model. But verification meaning not only on the data or on the model or on the performance of this model, but in all 3 aspects of this kind of thing. So in essence, verification tells you, does the whole thing work? And then if you can interpret your performance, which would be the desired thing to do, you ask yourself, why does it work? So this is a simple top-level concept that people are using, some people are using at least. And then in terms of data verification, we have the so-called benchmark datasets. And I am giving here a couple of datasets on flares. The whole thing about benchmark datasets is that you go ahead and you compare between different methods on the exact same identical data. So you validate the different methods against each other, because validation without identical data to train and test does not work. So this is something that we need to keep in mind. And to create identical data conditions, we need to have benchmark datasets that are curated, that are the best we can get, so that we can sharpen our skills, test the methods, and compare between the results of the different methods, as these would allow us to make both statistical and physical conclusions coming out. In terms of performance verification, this is a zoo. And all these kind of things are coming pretty much from either the reliability diagram that I mentioned before, or that little seemingly innocent table of 2x2 confusion matrix. You have a whole basket of metrics that you have to evaluate, not necessarily use each and every one of them, but know which one to use. And in order to know which one to use, you need to know your data. For example, in case of extreme class imbalance, which is the case with solar eruptions, you need to know what to use and what not to use. Do not touch the so-called accuracy in this case, because it's going to give you 1, which means perfect. but this is not the case. Do not try to use both the Heidke skill score and the F1 score because they're going to give you the same values, and you're going to be perplexed because they are in principle different, but they collapse on each other because of class imbalance. You have all sorts of peculiarities. So you need to experiment, you need to know what you're talking about, and you need to know the nature of your data. And then another very important message is the self-consistency in terms of horizontal expansion, in which case you're adding more data and predictors and features in your data set, the same way you have created your benchmark data set to address the same problem with better statistics, with better terms. Or you can move a step further into a vertical expansion, in which case you're adding columns to your data sets in order to be able to take on different problems but related ones. So from flares to CMEs to SCPs. And here is an example over here. This is a list of flares, just a list of flares. You can have this list, to a very large extent, of course, many more events in order to do your prediction. This is going to be flare prediction. But what happens if you add some columns that give you an idea about CMEs, their speed, and whether their CMEs were shock fronted, and whether these CMEs were associated to SCP events. In this case, you can take your initial benchmark dataset, upgrade it into something that is being made with the same principles, and move on to different problems related to the one that you're dealing with self-consistently. So this is the full-fledged problems of flares to CMEs to SCPs, and these are some intricacies in terms of rarity. SCPs are in essence extreme events. We are talking about hundreds of C-class flares in order to get one SCP event. But if you're talking about fast and halo CMEs, halo meaning they are coming all the way toward you on Earth, in the present case, then almost one every 2 cases you get an SCP event coming out of that. So this is what we are looking for. And these are some meaningful studies that go all the way back to the photosphere to correlate things and help these models work. So there is a lot to be done in this situation, and there are efforts already. This is an effort that is currently in progress at Georgia State University, in which case people are putting together a 2-tier SCP model, forecast model, all the way from the solar photosphere. So you go from active regions to flares, to CMEs, to SCPs, self-consistently by using benchmark dataset and by taking into account, by putting your physics into your intricate details and connecting details between the different levels and tiers. We are talking about an SCP watch and an SCP warning in terms of pretty much like terrestrial phenomena like hurricanes, because people tend to understand better these kind of things, but we're trying to follow the same rationale, the same reasoning in order to come up with that. What does the future bring us? Well, the future in this case would be observations, routine observations beyond the Sun-Earth line at L4 and at L5. There are discussions at both sides of the Atlantic, at least, both in NASA and in ESA and the UK Space Agency, and there are already mission concepts that have been proposed, published, and are being debated in panels and commissions of the different space agencies. So this is my last slide. What did I tell you overall? First of all, I try to be firmly rooted in physics of solar eruptions. But if we are to become useful to the society and space exploration efforts, then we need to get a step further than pure physics. And this step is too important to leave in solar physicists alone. We need expertise. We need all the expertise we can get, at least in 3 different topics, namely in terms of data science, computer science, and statistics. Each one of them with a very well-defined role in terms of predicting solar eruptions and their repercussions to geospace and to other parts of the solar system, that is. Predicting solar eruptions by ignoring the sun does not work. We have seen some efforts that are perhaps dictated by simplicity, perhaps dictated by a decreased level of complexity. Yes, that's fine, but all in all, if we are serious about solar eruptions, at least in my mind, we should be getting all the way back to the sun. Predicting solar eruptions, moreover, is modular and can be taken on in steps, provided that we are keeping the self-consistency in place and provided that we have a seamless transition between the different spatial and temporal scales that I talked to you about. We are talking about 8 orders of magnitude, and this is already an intimidating problem to deal with. But we have to do it. And in this, we have a few simple but powerful weapons, which are the self-consistency and the effort to go through different spatial and temporal scales effectively. So all this is not written in stone, of course. This is nothing. There is nothing finalized. Things may change. This is kind of a disclaimer. But this is a proposed action. This is a proposed course of action that appears to be bearing promise, at least to the minds of many of us. The future will show, and it's good that we have different efforts, sometimes redundant, but nonetheless complementary in another number of cases, so that to see how far we can go and whether indeed it is possible to go as far as to protect our vital assets on the surface of the planet and in space, both the cislunar space and beyond in the deep space. And that's all what I had to say. Thank you very much for your attention, and I'm open to any questions you might have.
Yeah, thank you very much, Manolis. That's a really nice presentation. So we open for comments, questions. Please raise your hand and probably unmute yourself and go ahead with the question. Yeah. So far, I do not I don't see any raised hand yet.
Okay, that might be a bit worrying. Either people got everything or they didn't understand anything at all. So.
Ji-Chang, please go ahead.
Hi, Manolis. I think it's a very nice, very intensive, comprehensive review about a prediction of the not only FLARE CMEs, but also SEPs. That's very nice. So my question is that I think we have been doing this kind of FLARE machine learning for many years. It seems to me it's like to already reach a kind of limit of plateau. So we have exhausted on the features of magnetic features of active regions. We have tried different methods to do it. So question is that what do you think, or your comment, what is the bottleneck? Or what can we do to move forward to further improve the prediction capability?
Right. So this is a key question, Z, and thank you for posing it. Indeed, I don't think to be sure. I don't think that we have exhausted all our possibilities there. The question is mostly a physical and a statistical one. The physical question is whether what we measure at the photosphere by the photospheric magnetic fields in which eruptions do not happen, as we know, they happen at least a couple of megameters above the photosphere. So these metrics on the photosphere, are they able to give us a picture that is credible enough so that we can forecast? This question has not been addressed in my mind. At least we see a method that works really well. In which case this question will have been answered. But so far we have not seen anything like that. So that's one thing. The second thing is redundancy. Just to give you an idea, in FLAREcast we calculated up to 200, more than 200 features predictors in each active region case, 209 if I remember well. Most of them are redundant with any method you might try. Same methods, different methods, excuse me, are going to give you different sets of parameters that appear to be working best. But I am talking about a small number. All in all, 10 parameters or less in supervised and hybrid schemes appear to be working better than the rest 190 of them. So there is redundancy in there. And you might say that, well, if I have those 10 parameters, then I know what works better. And the truth is a little bit more complicated than that, because in principle, different methods are going to give you different sets of best performing parameters. So in essence, we're getting back to square one and we try to understand. Yes, there are some patterns here and there. These are hardly investigated yet. So by no means we have exhausted our possibilities in there. We need to think and we need to show whether the data we are using are the data we should be using, or we should go to something else. And second, we need to find out a scheme that is makes most sense in terms of physics, and then follow on the best performing parameters on this scheme to try to make things advance. I hope I addressed your question.
Thanks, that's clear enough. Thanks for that.
Okay, good. Maria, please go ahead.
Hi, Manolis. Nice talk. So I
Thank
have
you.
quite, so when you try to predict flares, you basically identify each, you assign to your active region either a positive flare flag or a negative flare flag. But we know that the active region is continuous, there is spatial information. So I was wondering whether we could include spatial information. For example, flare ribbons tell us exactly whether a given field line would participate in the flare or not. So is there any way we could advance our models by trying to predict which specific fraction of the active region would participate in the flare using all these nice advanced methods that you've mentioned? And this might also help us to distinguish between a confined flare or eruptive flare, because some recent statistical studies have really shown that the fraction of the active region that participates really defines whether the given flare would be confined or eruptive.
Yes, that would be fantastic, Masha, if you had a way to quantify whatever information you have in there. So flare ribbons is one thing. You might take the reconnected flags in these flare ribbons, or you might take the length, or you might take the width of these ribbons. Any number that makes sense and you can use into a method, because these methods, whatever they are, they do not take the physics, they take the numbers. So we try to put all the physics we know into these numbers. And I totally agree that any number that goes a bit above the photosphere, closer to where eruptions actually happen, closer to where they actually initiate, might be able to help. So I have not yet seen cases like this, but it would be a very good idea. There are cases in which, for example, Mariana Corsos has published an idea on three-dimensional flare forecasting, which I think is promising. Anyway, we can go a bit beyond, you know, the two-dimensional solar photosphere and stopping trying to guess the three-dimensional monster in the corona by just looking at its footprints at the photosphere, because this is not happening, as Parker once said. Anyway, we can involve three-dimensional information would be meaningful, provided that it is compliant to the physics we know.
Thank you.
Sure.
Okay, good. I saw one more raised hand, but it disappeared.
Okay, I can ask that question. Sorry, that was my hand.
Okay, go ahead.
So first, thank you very much for the talk. I mean, it's very interesting. I learned a lot. I mean, I'm very new to this. Just a general question, because at the beginning you mentioned that this is a stochastic process, right? If that's the case, I mean, you also said in the slides it will be difficult to predict. So, and the later part, it seems like we are able, I mean, and many results literature shows we are able to predict. So what's your understanding about this? It is truly
Yes.
stochastic, yeah.
So this is a great philosophical topic, Xiaowei.
Thank you, yeah.
Idea is the difference between randomness and stochasticity. So it is not randomness, it is not chaotic, it is a stochastic process. Stochastic meaning that it is deterministic, provided that you can look into the correct spatial and temporal scales. And even though we might be able to look into the correct temporal scales, we are by far unable to look into the correct spatial scales, which is the magnetic reconnection scales. We observe at much higher spatial scales. Just to remind you, the 0.5 arcsecond per pixel for example, the HMI or the AIA in Solar Dynamics Observatory is just 350 kilometers, whereas magnetic reconnection scales are a kilometer or sub-kilometer, if we are to believe what the theory is telling us. So in this case, we do not have all the information, and we might think that an active region or a magnetic configuration in general is ready to erupt at any time. But we do not have all the information in our hands. We do not have three-dimensional information, and we are unable to look at the correct scales. So this is stochastic. And by stochastic, we mean that we have to assign a probability next to the guessed or projected occurrence of an event, to just account for this stochasticity, a probability that might be conservative or a bit more liberal, or any way we calculate it, but a probability nonetheless. So this is stochasticity and the way it appears in there. This is how people have thought of it in case they, in those efforts that associated active regions with self-organized critical systems. Stochasticity means probability. How well this probability will be working, again, depends on the physics, the homework we have done, the physics, the statistics, the data science, and the data mining.
Very clear answers. Thank you so much. Yeah, thank you. I appreciate it. Very clear. Yeah, thanks.
Mm-hmm.
Okay, thank you very much. Thank you all. Thank you, Manolis, again for your nice presentation, and hope to see all you again. Yeah, thank you very much. Bye.
Thank you for your attention. Bye-bye.